Hello and welcome. Today we're going to dive into something that's really at the heart of chemistry. What makes a metal a metal? And what makes a non-metal, well, not a metal? Let's get right into it.
Okay, just think about this for a second. Why is gold so shiny and valuable, while a lump of coal is just dull? And why can you shape gold, but if you hit coal, it just shatters into a million little pieces? That single question, that's the key. It gets right to the heart of the epic showdown between metals and nonmetals, and that's exactly what we're going to explore.
All right, first up, let's start with the super obvious stuff, the things you can literally see and touch. We're talking about their physical properties, which is just a fancy way of saying, how do they look and feel on the outside?
So the very first giveaway is something called luster. And really, that's just a word for shininess. Metals, they've got it. You think about gold, silver, copper, they all have that classic, brilliant shine. But nonmetals, not so much. Things like sulfur or the carbon in coal, they're usually pretty dull. No sparkle there.
And it's not just about looking good, right? It's also about how they behave when you put them under pressure. Metals have these two really cool properties. They're malleable and ductile. Malleable means you can hammer them into super thin sheets. Think aluminum foil. Ductile means you can stretch them out into long, thin wires. Hello, copper wiring. Now try doing that with a nonmetal. No way. They're brittle. You hit one with a hammer and it doesn't bend. It just shatters.
Now, this next one is a huge deal, especially for, all the technology we use every single day. We're talking about conductivity. Metals are amazing conductors of both heat and electricity. It's no accident that your cooking pans and the electrical wires in your home are made of metal. They let that energy flow right through. Nonmetals do the exact opposite. They're poor conductors, which actually makes them fantastic insulators. They stop the flow of energy.
But just when you think you've got all the rules figured out, chemistry loves to throw a curveball. And that curveball's name is mercury. It's a metal, for sure, but while pretty much every other metal is a solid, mercury is just hanging out as a liquid at room temperature. It's the ultimate rule breaker, a total rebel of the periodic table.
And the rebellion doesn't stop there. We just said nonmetals are poor conductors, didn't we? Well, say hello to graphite. You know, the stuff in your pencil lead? It's a form of carbon, which is 100% a nonmetal, but guess what? It's actually a good conductor of electricity. It just goes to show you, in science, the exceptions are often the most interesting part.
And just to round out our collection of oddballs, there's bromine. If mercury is the liquid metal, bromine is its nonmetal twin. It's a liquid nonmetal. So what this tells us is that nonmetals aren't just solids. They can be solids, liquids, or even gases.
Okay, so we've talked about the outside, how they look, how they feel, but to really get to the heart of what makes them different, we have to go deeper. We need to look at their chemical personality. This is where we see their true character.
So what's the big secret here? What's the one thing that explains everything? It's actually incredibly simple. It all comes down to a game of give and take, with these tiny little particles called electrons. Seriously, that one action, giving or taking an electron, defines their entire chemical world. Let's start with metals. You can think of them as the generous givers of the chemical world. They have a few electrons on their outer shell that they are more than happy to lose. And when they give away those negatively charged electrons, what's left behind? A positive charge. That's how they become a positive ion, and it's why we call them electropositive elements.
And if metals are the givers, well, you can probably guess what nonmetals are. They're the takers. They love to grab those electrons that metals are so eager to get rid of. And when they gain those extra negative electrons, they become negatively charged ions. You see? You've got givers and you've got takers. It creates a perfect balance. This whole giver versus taker personality totally changes how they react with other stuff, like the oxygen in the air. When metals team up with oxygen, they typically create something called basic oxides. But when nonmetals do it, they form something completely different, acidic or neutral oxides, two totally different outcomes from the same reaction.
And you know what's coming, right? Another fascinating exception. There are these special metal oxides called amphoteric oxides, and they just can't decide which team they're on. A perfect example is aluminum oxide. It can act like a basic oxide and react with an acid. Or it can act like an acidic oxide and react with a base. It literally plays for both teams.
So, how do we know which metal is the most generous electron giver? Well, chemists came up with a really useful tool called the reactivity series.
Honestly, just think of it like a sports league table for metals. The ones at the very top are the superstars, the most reactive. And they're so reactive they can actually kick out or displace the less reactive metals below them in a chemical reaction. It's a total power move.
Okay, so we've covered their physical nature and their chemical nature. Now, for our last section, let's connect all of this to the real world. How do these properties affect everything from a rusty gate to the coins in your pocket?
One of the most visible real-world impacts is corrosion. It's that natural, slow-motion process where metals just get eaten away by their surroundings, by reacting with things like moisture and gases in the air. The most famous example, of course, is iron forming rust, but it's also why silver can tarnish and turn black over time.
But we can use chemistry to fight back. A really common method to stop rust is called galvanization. It's such a clever trick. What you do is coat an iron or steel object with a thin layer of a more reactive metal, like zinc. The zinc basically acts like a bodyguard. It corrodes first, sacrificing itself to protect the iron underneath.
But the story of metals isn't just about decay and prevention. We can also intentionally mix them to create brand new materials with way better properties. And this brings us to the wonderful world of alloys.
So what exactly is an alloy? Well, it's a uniform mixture of two or more metals, or sometimes a metal mixed with a nonmetal. The whole goal is to combine the best properties of each ingredient to create a new supermaterial that's stronger, more resistant to corrosion, or just has other cool features.
And you are surrounded by alloys every single day. Brass, which is used in musical instruments and all sorts of fixtures, is just a mix of copper and zinc. And bronze, famous for statues and medals, is made by mixing copper and tin. It's a perfect example of how we can engineer materials for very specific jobs.
And there's even a special name for alloys that used our rule-breaking liquid metal from earlier. If one of the metals in the mix is mercury, the alloy is called an amalgam. These were historically really important, especially in dentistry for making fillings.
So what's the crucial point here? The big takeaway? When you boil it all down, everything we've talked about, from the shine of gold to the rusting of iron to creating strong alloys, it all comes back to that one simple fundamental choice: to give an electron or to take one.
And that leaves us with a final thought. If we can master these properties to create entirely new materials like alloys, it really makes you wonder, right? What other fundamental rules of chemistry are out there just waiting for us to explore, bend, and create something completely new with? Something to think about. Thanks for joining me.